All right, welcome back, everyone. My name is Dustin, and this is going to be the start of a new series I want to try out, where we're going to take a look at modern C++ and some concepts that may look complicated and try to see if we can make them more simple or obtain a better understanding, okay? So for today, we're going to be talking about something that confuses a lot of people and a lot of beginners, pointers. But we're not just going to be looking at raw, regular pointers. We're also going to take a look at smart pointers. So grab your coffee, your favorite IDE, and let's get started. Before we can dive into smart pointers, we have to answer the question, what is a pointer? So a pointer is a variable that holds the memory address of another variable. Instead of storing the actual data, it stores a reference to a location in memory. Basically, it points at the location that holds the actual data that we care about. Let's take a look at an example. Let's actually put all the stuff for raw pointers in its own little, we'll just say raw pointer example. And we can just call this function right here. Awesome. Okay, so for the first one, there we have a variable. And we go int value is equal to 47. We can create a pointer to this by getting the address of this variable. So we can go int pointer, and we'll just call this ptr1, and that is equal to the address of value. We need to use the ampersand in order to get the address of this variable. So if we print this out, we can go std cout, and we can print out the stack address. The reason why I say stack address here is because this variable was declared on the stack. As you can see, we didn't say new or anything like that, so we declared this on the stack. I'm going to say stack address, and that is equal to ptr1 std end line. So if we run this, this should print the stack address of this pointer, or the place in memory that this value was stored. Let's run it. All right, as you can see, we have that address there. And if we keep running it, that'll be a different value each time, because it grabs that value. It doesn't grab the same value each time. It grabs whatever area of memory that is open that it can use. We want to see the value of what is stored at the address. We need to dereference the pointer. So we can just copy this line down. And to dereference it, we use this here, the star. And then we just say, we can change this to value. So that's the address of the value variable. And this is the value that is at that address. And that's really it. A pointer is just an address in memory. Well, a pointer is a variable that holds on to an address in memory. It's not the address itself. And you can also have pointers to pointers, because a pointer itself is a variable, right? So this will have to have its own memory location as well. So say we go int so here, as you can see, we have a pointer to pointer, and they're taking the address of this pointer. Okay, so if we copy these, paste this here, and then we'll say stack address of, let's take the address of ptr1, and then copy this down again, and then we'll take the value p2p, and if we take this here and go dereference p2p. So as you can see, these two stack addresses here are both the same location in memory. And this pointer 1, is pointing to this location in memory. And if we dereference this, or pointer to pointer, that shows what this one is pointing to. Okay? So our pointer to pointer, it holds the location. And if we take it twice, we'll actually get the value of this pointer here. As you can see here, so our pointer to pointer, and if we dereference it twice, we get the value of this variable. Awesome. So let's just say pointer to pointer. All right. And we'll keep going. Now, pointers are a very powerful tool to have, but they can be kind of tricky. If used incorrectly, they can cause memory leaks, dangling references, and crashes. That is why modern C++ introduces smart pointers to make memory management much easier and safer as well. However, looking at this example, it was an example of a raw pointer. However, we're just pointing at a value that's on the stack. So we're not really doing any memory management here. In order to actually do some memory management or to worry about memory management, we're going to have to actually allocate something onto the heap. And for us to do that, we have to go int pointer, and we'll say ptr2. That is equal to new int, and we'll say 65 or 64. That works. Awesome. And if we copy all this stuff here, we don't need both of those, but we can copy this here. And this is not going to be stack address anymore. This is going to be our heap address. Change this to ptr2. And the value is going to be ptr2. Now the problem is we have allocated this onto the heap. So we need to make sure that we handle that memory, okay? Because that memory was given to us and that we were given a pointer to that memory. Now we have to make sure that we free it or delete it. In order to do that, we use the delete. And then we go ptr2, and then we should be all right. Okay, so let's actually just quickly comment this out. Actually, no, we'll keep that. And we'll just put in some separators so we can just go std, cout. Cool. So we'll take this and we'll just separate it like that. So actually, let's fix this up a little bit. Let's say stack address, and let's say ptr1, p2p. Awesome. All right. And then we'll run this. Okay, cool. So this is right here. And it shows that we now have a new object allocated upon the heap, and its value is 64. Pretty easy, right? Now this is working. That's great. But here's the problem. What if we forget to actually call delete? Or what if you have a function that throws an exception before it reaches the delete? This is where you will get a memory leak. Let's actually do a quick example where we forget to call delete. And we'll make a new function for that. We'll do that up here. And we'll just say void bad memory. And we'll just say, actually, let's return int. And then we'll just say int pointer ptr is equal to new int 978, sure. And then we're going to return the dereferenced pointer, or to get the value of the int that we just created. Now, anyone can see here that we didn't delete the value. We asked for some new memory from the heap, and then all we're doing is returning. So if we run this right here, we're actually going to end up with a memory leak. Now, it doesn't really matter in this case. As you can see, it ran through and it didn't do anything, right? Now, we're not doing anything with the value, so let's go std cout bad value. Grab this as well. Sure. And we'll run this. Because the program ends right away, all the memory and everything is released anyway. So that's okay. But what happens if we're always calling this function, or we're calling it many times? Let's see what happens here. So let's actually go here, and let's just put this into a while loop. Let's go while 1. And we'll just throw this inside of here. And let's run it and see what happens to our memory. Okay, so it's running constantly. Let's take a look at our diagnostic tools. And look at that. See, it's constantly going up and up and up and up. Now, it's only an int, so it's going pretty slow. It's not that heavy of data. But this is going to keep going up until we have exhausted all the memory that this program has been allotted for. And then it's going to crash. And then we're going to have to find the memory leak. So that can be the problem with pointers. Let's stop this. So the issue here is, if you take a look here, we declare this pointer. Now this pointer is on the stack, right? We declare this pointer and we allocate some new memory, and then we're returning right away. However, we don't have access to this pointer anymore. So what's happening is we don't have access to the value or the address where that memory was allocated. So we can never actually free it. Let's actually not call this function just so you can see. We'll leave this function as an example for the increase in memory. And we just comment this out so we're not actually calling the function. Let's run it, and then let's take a look at our diagnostics again. So now it's running like crazy. But if you look at it, it's steady. Why? Because any memory that we're allocating is automatically being freed, and we're okay. So we'll have no problems with memory management there. All right, so this example is pretty silly, and you would probably notice it right away. So if you remember, a pointer is just a variable that points to a memory location. If we no longer have that pointer anymore, we have no way to remove or delete that memory at that location. So your program will just keep using more and more memory until it eventually crashes. Not cool. That's where smart pointers come in. Are raw pointers always bad? Well, not necessarily. There are times when you should use raw pointers. Here are some times that you should use one. If you're working with low-level APIs like OpenGL, Vulkan, or certain system calls, that's always a good time to use a raw pointer. Also, if you're dealing with performance-critical applications where manual memory management is necessary. Also, when you're interfacing with legacy C code that requires raw pointers, you're going to need to get the underlying pointer if you're using smart pointers, and we'll get into those legacy functions later on. Raw pointers can be a force for good. However, just remember, if you are going to use raw pointers, manage them carefully. Otherwise, use smart pointers to make your life easier. So the first one up for the smart pointers that we're going to be looking at is the std unique pointer. All right, so let's actually start. Let's make a new function here. We'll say void unique pointer examples. Cool. And you can declare a unique pointer like this. You can go auto, and we'll say ptr1 is equal to std make unique int, and we can say 87. Cool. So what this is going to do is create a pointer for us, and it's going to be a unique pointer. Now the auto here is just so I don't have to write unique pointer int again, because it's already being done here. But the cool thing about this is it's automatically, we don't have to worry about deleting this. It's going to delete it automatically. So let's actually comment this out and write the unique pointer examples. Unique pointer examples. And let's actually just do the same thing. Let's go std. Let's grab this stuff from up here and see what the address is, and it would be a heap value and the value itself. Paste this in here. This is pointer 1, and it's done the same way. Pointer 1 dereference. Okay. So what this is going to do, it's going to show us the address that this is at, and then it's going to give us the value at that. What's great about unique pointers or smart pointers in general is as soon as this goes out of scope, it's going to release the memory that was allocated here. And we can prove this by showing that we're not calling delete, but we're going to run this in the while loop, and our memory shouldn't increase. So let's run it. So it's giving us the addresses. Now the addresses are changing this time because every time it goes through the scope here, every time it runs through here, it's grabbing new memory from the heap. And that's going to be at a random location, or well, whatever location that the computer chooses to use or the program chooses to grab. And if we go to the diagnostic tools, as you can see here, bang, nothing. Nice and flat, not increasing at all. Not like this one up here, the bad function, where we forgot to release the memory or delete the memory. This one's running fine. Awesome. So that's one of the major benefits of smart pointers. Automatic memory management. It helps you out big time. Okay, so let's stop this. So why is this called a unique pointer? They're called unique pointers because they ensure exclusive ownership, meaning only one unique pointer can manage an object at one time. So what that means is you can't copy it. The only way that you can actually pass along these pointers is you have to transfer ownership. We'll go over that right now. So let's see. So let's make another pointer. We'll go auto ptr2 is equal to ptr1. Now, as you can see here, we automatically get an error. Now this is trying to be, so auto still works, and because it sees, oh, you want it to be a unique pointer of an int. Cool. The only problem is you can't make any copies. You're not allowed to copy these. Okay. The only way that we can handle this is using std move. We go std move. So what this is doing is we're transferring ownership from pointer 1 into pointer 2, right? What that'll do also, that will make sure that pointer 2 now is the owner of this memory that was allocated up here, and pointer 1 will become a null pointer. So let's check that out. Let's say if not ptr1 std cout ptr1 is invalid, memory has been moved. Actually, we don't need that there because I got a string. I can go here. Cool. And we automatically get this warning, and it's saying use of a moved object, ptr1. So this object has been moved. So the compiler already knows ahead of time that we're trying to use something that will be invalid. So it's letting you know. So, but we're putting that check anyway. Then we can say if ptr2 is valid, let's take this and go heap address and the value. And we don't want that. We want 2. Change this to 2. Now, because the ownership was transferred, it should be the exact same as these values here because it transferred this. Whatever was in pointer 1 is now in pointer 2. The ownership has been completely transferred, okay? And I don't want to run this in a while loop, so we'll just pull this out. So I just want to see how it works. Well, that's not going to work. It's going to be stuck in this while loop. So let's actually just comment this out totally. Cool. And run it. Awesome. As you can see, the addresses are the same, the value is the same, and the pointer is invalid because the memory has been moved or ownership has been transferred. Let's actually change that to ownership has been transferred. I think I spelled that right. All right, so that's the unique pointer. Great to use if you want to have concrete ownership, like there can be only one owner to this object. That's when you want to use a unique pointer. However, since we're already here, we might as well take a look at that legacy function stuff. Let's make a new function up here. Yeah, we'll just do it right here under bad memory. And we'll say void, we'll call this legacy C function. It might not be a C, but it's going to be a legacy style that takes a raw pointer. Right away, the first thing I'm going to want to do is just go std cout value before, I could say dereference the raw pointer. Now, I'm not doing any checks here to see if it's a valid pointer. I know it's going to be because we're setting it up down below. We're just doing this as test. So now we want to do after. So I might as well just copy this line down and then we'll say value after. Actually, let's do that outside. And we'll change the value. We'll say std cout legacy function running. And we'll change the value. Say dereferenced raw ptr equal to sure. And down here, we'll do this in our unique pointer example. So right here, let's say value after. Let's create a new unique pointer for this. Let's grab this. And we'll put this here. And we'll say std cout running. Cool. And let's create a new pointer for this. So we'll say auto pointer 3 equal to std make unique. And it's going to be int again. And it's going to be 978. Cool. And now we're going to run the legacy function. So in order to run the legacy function, we just say legacy C function. And it's going to need a raw pointer. We can't just pass the pointer 3 in there. It's not going to work. So in order to do that, we need to go get. That will get the underlying int pointer from this unique pointer. Let's put that there, and we can say std cout after ptr3, and let's go dereference it. Awesome. Let's run it. Awesome. As you can see, the value before, we sent in our raw pointer, adjusted it, and then the value after the legacy function. So this allows us to work with older APIs while still benefiting from smart pointers, automatic memory management. So just be careful not to store this raw pointer beyond its scope, because the smart pointer will go out of scope and it's not managing, or it's not looking for who has a raw pointer for it. So just be careful when you're using that. Okay, so next up we have the std shared pointer. And unlike unique pointer, multiple shared pointers can have shared ownership of the same object. The object is only then deleted when the last owner goes out of scope. So what it does is it keeps a count, or a reference count, of how many shared pointers are pointing at this object. So let's actually do some examples for that. We can go void shared pointer examples. And just like a unique pointer, we can do the same thing. We can just go up here, copy this, paste, and change this to a shared. You know what's interesting? This never asked me to add in memory here. So sometimes if it doesn't run, you're going to have to include memory. But it looks like Microsoft allows you to use whatever, which is a good thing. So this is going to do the same thing. It's going to create a shared pointer on the heap, and it's going to get rid of the memory, automatically delete memory as soon as it goes out of scope. Since it's the only one pointing at it, we know it's going to be deleted right away. And let's actually change this a little bit. So instead of saying heap address, let's say ptr1 address, and then we'll say ptr1 value. That's going to give us the address of ptr1. And we also were talking about a minute ago that it has a reference count, or a count. So we can go std cout, and we can say ref. And that's going to be ptr1 dot use count. Awesome. Remember what I said as well. These will automatically remove themselves as soon as it goes out of scope. So these pointers that were declared up here, besides being moved or ownership transferred, as soon as it goes out of scope here, they're automatically going to release their memory. Well, when it comes to shared pointers, it only releases the memory when the last owner goes out of scope. So if we create a scope here, a new scope, and create a new pointer, we go auto pointer 2 is equal to pointer 1. It's not giving us an issue because you're allowed to copy or add ref count to your shared pointers. So if I copy this here, paste, this is going to give us our ref count. So we're just going to follow pointer 1. It's going to follow its ref count. And then we're going to change this to ptr2. And we're going to change these to ptr2 as well. So what's going to happen is our use count is going to increase here, and it's going to have the same address. These values are going to be exactly the same. So what if we create another scope in here as well and do the same thing, and just copy this, paste, and just paste these in, change this to pointer 2, change this to pointer 3. So we have a new one. Keep pointer 1 just so we can see its use count. Change these to pointer 3 address, and also change this to pointer 3. Well, what's going to happen is, well, we have another one. Even though it's in a new scope, it's going to increase the ref count, okay? But if we copy this line, just this one, and paste it here, well, what do you think this value is going to be? So since we leave the scope here, it's actually going to decrement the use count here. So it should actually only be 2 here. And then if we do it again outside of this one, it's going to be 1, and we'll call this the final ref count. And let's run this. Oh, well, it's not going to do anything if we don't put this in where we need it to be. So let's take this and instead of running this one, paste this, and we'll run the shared pointer examples. Awesome. They all point to the same address. They all have the same value, but look at the ref counts. So the first one here, it's 1. Then it comes down here, and it's 2, and then 3. And then on the way out, it's 2 again, because it released this value. So this pointer no longer holds anything as soon as it comes outside of the scope. And then once it comes out of this scope, we check the ref count again, and our final ref count is 1. Once this goes out of scope, or pointer 1 goes out of scope, it will also be released. And we can prove that by just running it in the while loop. Let's go back, and we'll copy this, paste this here, get rid of this comment, run this. It should never get to there, so that's fine. All right, run this, and it should just keep going. So it's just running it, grabbing different memory addresses, and it should be deleting them all. Let's check our diagnostic tools, and bang, it's not doing anything. Nice and flat line. It's doing exactly what we need. Good stuff. Okay, so that's great. But we also, not only can shared pointers be copied like this, so it's copying. Every time you copy, you add to the use count. They can also be moved, or you can transfer the ownership of shared pointers as well. So let's go and say shared pointers can also be moved. We can transfer ownership. Cool stuff. So let's create one and go auto transferred. I'm not sure if that's right. How to spell transfer. Sorry. And we can go std move ptr1. And we're going to want to copy this stuff here. Let's copy it all. And we'll paste this in here. And now I'm going to say, let's get rid of this ref count for now. And let's say the transfer address is going to be the transfer or transferred pointer, what we'll call it. Transfer pointer. Yeah, there we go. That's better. And let's go with the transfer value as well. Transfer value. So what I also want to do is go if not ptr1 std cout shared pointer ownership has been transferred. End line. And now we can check the transfer count. So if we go, let's actually copy this ref count, bring this down, and right away the compiler knows this has been moved. Paste this in here, and we can say transfer count. Change this to transfer pointer use count. All right. So if we run this, oh, that's not good. Stop that first. Let's comment this out again and show the transfer. As you can see here, this value was empty, and so it called the shared pointer ownership has been transferred, and our transfer count is now 1. After that, then we're actually deleting the memory. Wonderful. All right, so finally we've reached the weak pointer. It's used when you need to reference a shared pointer owned object, but don't want to affect its lifetime. The weak pointer is actually great for preventing cyclic dependencies between shared pointers. Two objects hold shared pointers to each other and they're pointing at each other. They will never be deleted because they always have a reference to each other. Using a weak pointer can actually solve that issue, okay? Let's actually do a quick example for that. In order to do an example for that, let's create a couple of structs. So we'll just say struct B, and we'll say struct A. And A will have a shared pointer to B, B PTR. And then we'll say A std cout a destroyed. So A has been destroyed. And we'll copy the same thing and do a similar thing for B. Copy this. And we'll do this here. B. B. A. And then we'll say B destroyed. Now, if we keep this as a shared pointer, these will never be destroyed. So let's actually create another function here. We'll say void. And we'll say weak pointer examples. Okay. And I can make two shared pointers, so I'll go auto. Now I can say A is equal to std make shared A, and then B. So now we have to set these values. So we can go A at B pointer is equal to B, and change this to A pointer, sorry. And B at A pointer is equal to A. Oh, this needs to be B as well. Sorry guys, I'm trying to go too quick. So the problem here, if we run this, these both are holding a reference to each other. So let's actually run this in the while loop. And we can say weak pointer examples. Let's comment this out. Don't need to worry about commenting that out, but we'll run this and let's see what happens. Okay, so it's not saying anything here, but we should be calling destroyed. So our destructors are never being called. Let's take a look at our diagnostic tools. Oh, look at that. It's flying. It's flying and it's into the gigabytes. Oh man, let's stop this. That's because these will never destroy themselves and you're constantly adding new stuff on the memory. We're constantly allocating because these can never actually get rid of them. So a way to do that or to handle that is to have a weak pointer. Let's make this one be a weak pointer. And we can keep everything the way it is. And if we run it, it should handle that. Let's run it. Bang, look at A, B, A, B, A, B, everything's destroyed because a weak pointer has a non-owning reference to a value. So if the value is not there anymore, it just deletes itself. And let's check out our diagnostic tools. Nice and clean. All right. Now there's some other good times to use weak pointers as well. However, I believe that this is good enough. And that's really it. So when should you actually use each type of pointer? So you're going to want to use a unique pointer when you want exclusive ownership to an object with no overhead. So you don't want anything else. This is not a shared object. You want exclusive ownership to this particular object. You're going to also want to use a shared pointer when multiple parts of your program need shared access to the same object, okay? And then you want to use a weak pointer when you need a non-owning reference to a shared object. And then don't forget about raw pointers. Those are always good to use as well. If you can avoid them, especially in C++. However, you're going to need them when you're interfacing with C libraries, performance critical code, or low-level APIs. And that's it, guys. You're now armed with a knowledge of smart pointers, and hopefully this gave you a better understanding of how to use them and when to use them. So say goodbye to memory leaks and undefined behavior. If you found this helpful, don't forget to hit the like button, subscribe, and make sure you also hit the notification bell for more C++ content. I'll see you in the next one. If you have any C++ topics that you want me to try to cover or go over, let me know in the comments below. And that's it. Take it easy.